See this later. So the idea behind it again is to complete the objectives. Notice there's 5 different objectives here. So it wasn't just about like measure once, figure out the correlation, and then you're done. There's a couple of different things we had to do in this process. So first, when we're looking at the forces on an object, either when it's at 0 velocity or changing velocity, we'll notice that the different motion occurs. So when it's 0 velocity, we know we're in a standstill. If it's constant velocity, we know that there's equilibrium or a balance of forces. But when the force that's applied exceeds the other force, we know that there must be some accelerated motion occurring here. So when we look for accelerated motion here, we want to think about that. We're really trying to measure the acceleration of the cart. So for the cart itself, if we had a motion detector, the motion detector can plot your position, your velocity, and your acceleration. And if I carefully read this part here, and I look at it, it says, look at its change in velocity. Its change in velocity. And if we look at the second data point, we see collect force, velocity, and time data. Notice it says collect force, velocity, and time data. So are you actually collecting acceleration data? Are you collecting acceleration data? The answer is no. I'm saying no for most, but the answer is definitely no. What are you doing to get acceleration, though?
You find the slope of the graph and various velocity points.
Correct. So the velocity graph is what's really important here. And the slope of the velocity graph will give you acceleration at a given instant. So that was the answer to your question before. Remember, we're trying to find out the force and acceleration relationship at different instances in time. So not over a long time period here. We want instances. So we are looking at the instantaneous acceleration or the slope of the velocity curve at a specific moment, not over a general time period.
But if the acceleration is uniform, wouldn't the force be?
If the acceleration is uniform, absolutely. Depends on how you set up your lab. It might not be for yours, it may be for some. So if you have the hanging mass and the cart's getting pulled, then that acceleration will be uniform, absolutely. But if you had a setup where you decided to use the bumper and you wanted to push it, and you want to physically vary the force that you're pushing it with, you could vary that force all in one run. You could let up, push a little harder, let up a little bit, and you can see the variation of velocity, and the force graph would also change as well. So it depends on the scenario you chose there.
The first one, if it's changing velocity 0, could you accelerate as you accelerate?
So if the change in velocity is 0, that's when you're going to be moving at a constant rate at some point. So when you're pushing the cart with your hand, if you push it at a constant rate like this, that would be a change in velocity of 0. But it's only once you get it moving, because yes, in the beginning when it's not moving, just to even get it going, you are accelerating it by default. So a lot of your graphs, you'll notice, well, first, let's take a look at some of the graphs, what they would look like. Let's draw them ourselves. Okay. So if we look at our graphs here, and if we were to draw what our graphs would look like, let's take a look at force versus time and velocity versus time. So I'm going to start in red. And in red I want to draw what the force time graph and the velocity time graph would look like if we had, let's say, a constant force applied. A constant force. Okay? So a constant force could be one of those 3 scenarios with the Atwood machine with the mass hanging over the pulley. The mass pulls down on this, causing a constant force and tension in the rope the whole time. What would a constant force graph look like? Good. Horizontal. So this is scenario number 1 again. This is the Atwood machine scenario. That's what the force graph would look like. What would the velocity graph look like? Good. It'd be an increasing velocity function. Now, assuming in this case we started at 0 velocity. But we know from calculus that it doesn't matter where we start, because what matters is the slope of the velocity graph, the slope. Okay, so this would be the scenario for the Atwood machine setup, where you have a hanging mass over a pulley that's moving this at in this case, with a constant force. And how do I know that force is constant? Because where is that force coming from? It's coming from the tension in the rope. So if I were to look at my diagram for this, here's my cart on a surface, here's the end, here's the pulley, there's the rope connected, and there's the hanging mass. So this hanging mass is physically pulling down with tension on that rope. That rope translates and redirects the force to be applied horizontally to the cart. So this cart feels the same tension the entire time.
When I think of like having a constant force, like it's kind of like just like dragging.
That's constant motion.
Yeah.
It's very different. That's a really good point. Because remember, what does force cause, Matt? Force causes?
Changing velocity.
So if the force is constant, your velocity is changing. If the force is constant, your velocity is changing. It's when the force is zero, the net force I'm saying. I keep saying force. And by force, I actually mean net force, right? For all these problems, I mean net force. If the net force were zero, then the velocity is constant. So don't confuse that. It's very easy to say like, oh, this is a constant force. No, this is zero net force if I'm moving at constant velocity.
Oh, because of yeah.
See what I'm saying?
Yeah.
I know it's kind of weird.
Change in
Because really, what am I overcoming by moving at a constant force? I'm overcoming
friction.
friction. Okay, that's the key to remember here. So I might be applying a force, but if my force is equal and opposite of friction, my force minus friction gives zero. And that would be this scenario, where I'm moving at a constant velocity like that. If I were giving it a force the whole time, and I applied a net external force, it would have to be accelerating. And that's what would happen in this Atwood machine setup. Because the tension applies a constant force, so this cart has to increase in velocity. And that's what we're seeing in the red line here. So this is the Atwood machine setup for the first one.
Would the x versus t graph be like exponential?
It would be parabolic. Be careful. Remember, it's not exponential. Yeah. Parabolic. Yep. It'd be, or quadratic, we would say for now. Yep. Absolutely. It would be a function of t squared. T squared. Yeah.
Would be horizontal acceleration.
Yes, because this, that's a great question. So Chris asked the following. Would the horizontal acceleration of the cart be the same as the vertical acceleration of the mass, the hanging mass? The answer is yes. They move as a system. Okay, these problems, the acceleration of this cart will equal the vertical acceleration of this cart because they're literally moving together. As this accelerates downward, this will accelerate to the left. Now, what is the acceleration of this going to be? And be careful. Be careful with your answer. Don't jump to the conclusion that I think you're going to jump to right away. If you keep your head right away, it's probably not right. Go ahead.
Negative 4.5.
I'm not asking for a number. How about that? What would the acceleration of this be? Give me it in terms of a relative value. A relative value. More than this number, less than this number, equal to this number. What do you think, Chip?
It would be less than 9.8
Nicely done, Chip. Can you explain why?
because there is going to be friction involved.
In general, there's an opposing
There's an opposing force.
opposing force. Very good. So, if I were to drop the slotted masses literally in the air, what's their acceleration? 9.8, right? Negative in this case. But in this case, because this mass is going to start to accelerate downward, it's not going to have acceleration equal to gravity because of this counterweight here, or this counter force that's pulling back. Okay, so keep that in mind. So when we look at this problem with the Atwood machine, we're going to see that something is going to slow it down. It's going to slow it down. Yeah.
I think there's too much force is going to be massive, right?
Correct. Yeah.
But it's the mass of one.
Well, no, sorry. The accelerate. Which mass are you asking about, Chris? This question.
Of both of them.
Depends. So if the cart's mass changes, if this cart's mass changes, it'll change the acceleration of the system. If this mass changes, actually, it'll also change the acceleration of the system. A change in mass in either scenario would change the acceleration. Yeah, and that's why I think in one of the objectives they ask about, the last one, the effect of mass on the relationship between acceleration and force. This last objective here, that's what that one is accomplishing, varying the slotted hanging mass and the mass of the cart.
So if you change one, you change all.
Yeah, but if you change them both at the same time, you can't see the effect of it, right? We need a control in the group. So we'd want to change either the slotted mass to increase the amount of weight pulling down, therefore increasing tension, or we want to change the mass of the cart, which therefore changes the mass of the system in a sense here, which changes the acceleration. Because think about it this way. The amount of weight pulling down here, right there, that weight pulling down, if that goes up and this mass doesn't change here, we've got MA for this guy over here. Well, if this suddenly increases a lot, God bless you, if this increases a lot and the mass doesn't change, then acceleration is going to go up. because this is causing acceleration. Okay, I'm not going through equations yet, I'm going through concepts here. Second, if the mass, in this case, were to go up a lot, and this weren't to change, if this goes up and this is constant, acceleration has to go down. Okay, because again, this is the overall force being applied to the system right here. The weight of this object is the force being applied to the system mass.
So if you know that the acceleration is less than 9.8, you also know the mass of the object. How do you calculate the acceleration of it if you know that if it is less than 9.8?
How can we calculate it?
Yeah.
In this problem, we'd have to look at the overall force acting, we'd have to know the mass of the cart, and then just divide the two of them. So it would be, yeah, this is what it would end up becoming, right? And then we would say this is the overall force acting on the cart, which in this case is just tension. That's the only thing acting, right? If I draw the free body diagram of the cart at the top, here's its free body diagram. There's tension, and that's it. There's nothing else. Yeah, I know there's friction normally, but in a problem like this, if I'm correct, I think it was a frictionless surface. I don't know if it was it given as frictionless? No, so we'd actually, well, the assumption is that these carts, where is it? Let's see if it said anywhere on here.
It's on the track, so that assumes there's like a low friction environment.
Yeah, it doesn't say it in the actual lab here, but it would be given on the AP exam either as having a friction coefficient and it would be sliding back and forth, not on wheels, or it would be given as a frictionless surface. If there were friction, then we would absolutely draw friction acting to the right. And I sometimes use, your book uses T, I have a tendency to use FT, force due to tension, FF, force due to friction. So I don't want to confuse you. I'm going to use FT throughout the year. I just put T there because I'm used to the book when I was reading on there. But yeah, that could be a scenario also if there were friction involved. In this case, though, because it's a track, we're not going to worry about friction being involved here. So this would become that FT is the only force pulling down. But if I look at the free body diagram of this guy, well, this has FG pulling down and FT pulling back up. FG pulling down and FT pulling back up. So we've got a free body diagram of this one, we've got a free body diagram of this one up here. We'd use both equations simultaneously here to figure out the acceleration of the whole system. What about another scenario, before I get into any more math? What about another scenario? So that's one scenario where you have a constant force being applied via the Atwood machine. What did you do in your arrangement that was different? Because I'm sure not everybody yet. Did everybody use the pulley? Yeah, so what did you do differently if you didn't use the pulley? Give me a scenario. Matt, go ahead.
I did the motion sensor and I pushed
Okay.
the cart.
So Matt used the motion detector to measure the velocity,
Yeah.
and then you used the force sensor and you pushed with it instead of pulling.
Yeah, so
Absolutely acceptable, and that's probably what I would do at first glance. That's when I read this lab, that would be the way I would actually go about it. Just because it seems intuitive in that nature. So tell me more about what yours might look like then, Matt. So what would be a scenario you gave, like with your force graph, if you had something here? Go ahead.
so set up the track and then using you'd be able to like calculate the force, and then using that you'd be able to find the acceleration if you knew the mass of the cart.
Okay.
Using like A equals F over M. And then like what else would you the graphs.
Yeah, tell me what you think your force graph would look like, or what scenario would you be going through? Would you, I mean, if you pushed, right, and you wanted to get it move at constant velocity, right, what would your force graph look like then?
With positive velocity.
Yeah.
Would it be 0?
Good. So the force graph at a constant velocity would look like this. And then what would the velocity function look like?
It would be straight line.
Yeah. So this is another scenario right here where you push with 0 net force. The force with which you push simply gives it enough velocity to overcome acceleration, but then move at a constant rate. Is this going to be the exact graph? Are we ever going to have a graph where it could look like this and we have motion? We have to have some initial push, right? So you'd probably have something where there's like that. There's a little initial force you give it to get it moving, and then once it's moving at a constant velocity, the net force acting on it would end up being 0. Yeah.
I was thinking like in my head, like if you just like kind of apply one quick thing and then you could calculate the deceleration using the motion sensor. Like would that also work, or would that not be? Would that be better?
Let me think for a sec. You mean push and then release, right? You're saying like give it a push and then move away?
So like if I was like that.
So what that would do is that would measure the initial push, the initial force you're applying, and then afterward the deceleration will come as a result of friction there. So if you saw the deceleration, you could eventually measure the frictional force that's acting from that deceleration. So that's a standard one in like a lab where you move something at a constant velocity or you then release it and see how long it takes to come to rest. You could figure out how long it takes to come to rest. You could have the initial velocity, the final velocity. Using final initial velocity and time, you could find acceleration. And then from that acceleration, you could then find out the frictional force. Using last chapter with kinematics, with this chapter and forces combined. Chip.
So, will the force on an object either be greater than or equal to than the derivative of velocity?
Well, we can't relate those two. One's a force, one's a velocity. What do you mean?
Well, because
Like I can't take a derivative of force and set that equal to velocity or greater.
sorry.
That's right. Just reword it.
So the acceleration is like the derivative of velocity, right?
Correct.
And then force is just the derivative of the velocity times the mass, right? It's
Force is the derivative of velocity times the mass. Yep.
So the force is either going to be greater than or equal to the derivative of the velocity.
Depends on if the mass is greater than 1 or not. Mass is greater than 1, then you take a number greater than 1, multiply with the derivative of velocity, and gives you force, right? But if the mass is 0.5, then 0.5 times the derivative of velocity gives you a number less than the derivative of velocity was.
Okay,
So there's no general assumption you can make either way. It depends on your mass. Remember, your mass is your constant in proportionality. That's what the mass is. The mass is the relationship between the derivative of velocity and the force. When you divide by the derivative of velocity, acceleration, you get mass. So it depends on the number. Notice though what you said is true. What's the derivative of this line right here, guys? What's the derivative of a constant function? The derivative is 0. 0 times anything is 0, right? And the force was 0 in this case. Again, I'm trying to think of another scenario. Anybody come up with something different besides just pushing and releasing, hooking up to a pulley, going over the edge? Or is there anything else unique or something different about your procedure that hasn't been mentioned? Or something unique about the data collection portion, or how you go about doing it? What questions you have right now? Something that's not really clear yet? So let's take a look at some data and think about what we would do then. How about that, okay? Let's look at some sample data if they were giving us data. So let's say the following data were given. Let's say this is going to be force, velocity, and time. Notice the 3 types of data I'm giving you here are the things that they mention in the actual objective function here, or the objective in this case. Again, collecting force, velocity, and time data as the card is accelerated. Then using graphical methods to determine the acceleration. So let's say our data is the following. Let's think. We've got, I'm going to make my time intervals consistent to make this work properly, right? I'm going to say my velocity is okay, all in standard units. Imagine newtons, meters per second, and seconds. So those are my values in this problem. First of all, given those values, which setup did we choose? Given the following values, all right, given the following values, which setup did we choose? Did we choose a push and release, or did we choose a push with a constant force, or did we choose a Atwood machine with a hanging mass? Which of those 3 setups did we choose? What are you thinking? What are you thinking? Chris, what do you think?
Try to push with constant force.
Try to push with a constant force, or it could have been The Aglet machine is also a constant force. Don't forget, the hanging mass pulling down is a constant force. So which one wasn't this? This was not the push and release problem. Okay, the push and release, remember, is shown down here at the bottom, where when we release, there's no net force acting on the cart, and therefore it's moving at a constant velocity after that push and release. So this is definitely the first scenario. Now, notice again that your force doesn't fluctuate too much. The idea is that it's a general value given here. So what might I do in a problem like this? What might I do? What might I do? How would I prove that this shows Newton's law? Yeah.
We can graph like velocity versus time.
Okay, so we did it. Got it. Go ahead. And that's right here in the middle, let's say for now. Here's the graph of velocity versus time. Here's the graph of force versus time. Let's say it goes from 1 to 5 seconds there, right? And the velocity y scale goes from 0 to 20 maybe. Or in this case, yeah, 0 to 20. And time equals 0 to 0. 0 up to 20, and then 1 to 5 on the force axis, and 0 to 2.5 versus 1 to 5 on the time axis. So there's my graphs right there. Let's make this, I'll make this 25 actually here. Oh no, actually make this 18, sorry. And we'll make this 2.5. All right, so there's my actual graph. Then what would I go about doing? How would I step through the procedure? What would I do? What would I do? And I can do this several different ways, so there's not just one answer. Give me a stab at what you think you would do at this point. How would you go about proving Newton's law from this? What do you think, Chip?
Well, maybe since you're trying to keep like the same force, you could take the average of the forces.
Okay.
And still keep consistency.
So you're saying an average of all 5 data points?
Yeah, yeah, for the force, yeah.
If we did the average of all 5 data points, right? I like that. Then we'd want to find what for this entire line? The whole slope of the whole line from beginning to end, which would give us really the average acceleration. So the average force and the average acceleration there would give us mass. That works. What's the other way we could do this? Instead of the entire force?
You could apply, you could plug in the values into the like after the limit equation to find the acceleration.
Specifically where though? In a given instant, right?
Oh yeah, yeah.
So I could use this scenario here, change in velocity over change in time gives me acceleration. And then I have the force of these two. I probably want to average these two though, because I don't have either one. So I can look at this at a bigger scale, or I can hone in on this and look at it on a small scale of my specific instances in velocity and force. Okay? Again,